Welcome everyone to the MIT Categories Seminar. Today we're lucky to have Michael Robinson from American University speaking to us about a paper recently published in Compositionality. This paper is Assignment to Sheaves of Pseudometric Spaces. So you'll be able to find this paper at compositionality-journal.org. And before we start, just a reminder about questions. Please feel free to ask questions as they come up. The best way during the talk is just to type a question into the Zoom chat room or the YouTube chat, and I'll grab Michael's attention at an appropriate moment. There'll also be plenty of time to ask questions towards the end of the talk. So without further ado, I'll hand over to Michael. Thanks for joining us.
Thank you. Thanks everyone for listening in. Thanks to Brendan and the organizers for the invitation to speak to you today. As mentioned, this is all discussed in a paper of the same title as the talk, and it's really a meditation on the geometry of sheaves through the lens of category theory. And you could think of this talk as being exploring some exotic categories that have some bearing on the geometry of sheaves. As is traditional, there's lots of people that I've been working with over the years thinking about these ideas. Here are a few of them. In particular, I want to call out Steve Huntsman and Cliff Jocelyn, who are two of my longtime collaborators on this kind of work with sheaf geometry and acknowledging funding from various different funding sources. Okay, so the key ideas for the talk today are that I think we should think about, rather than thinking of sheaves of sets or sheaves of abelian groups or that sort of things, as is traditional, to think about sheaves of pseudometric spaces and study their geometry. Now, one of the things that comes out of that is a notion of a filtration, but not of a filtration of a topological space, but rather a filtration of a cover of a topological space. That turns out to be a really useful concept for understanding the geometry of a sheaf and understanding the geometry of an assignment, some data picked out of that sheaf. And I think these are interesting objects in their own right, these filtrations of covers. And so they kind of have a dual categorical and topological nature. On one hand, there's some functoriality, and on the other hand, there's some topology. And so that's really kind of neat, although a big caveat is I'm really only interested in finite topological spaces. The reason is that most of my applications are very combinatorial and very computational. And that also helps because it makes the mathematics work a little bit better. I think many of these ideas generalize to more general topological spaces, but I haven't been motivated to go that direction because of my applications. So the context is that you've got some data, you've got a model, and you want to sew them together and understand how the data and the model fit. There are a variety of techniques that you might try to do this. So very popular these days is topological data analysis. Its main tool is persistent homology. And the disadvantage is it's fairly sensitive to outliers. On the other hand, statisticians love outliers and love understanding them. And their typical statistical tools are somewhat less sensitive to outliers. But generally speaking, the topological structure that's present in statistical tools tends to be a little bit more basic. A lot of the machine learning ideas that have become popular tend to offset that weakness, but still the topological structure tends to be not the main idea. And what's nice about sheaf theory and sheaves is they mediate between these two extremes. You can capture the topology, and you can capture the geometry, and you can manage this interplay between topology and outliers. Now, the thing that comes out of a sheaf geometric analysis of your data and models is something that I've been calling the consistency filtration of a sheaf assignment. Now, those are in italic because they're defined terms, and I want to show you how they work, and I want to give you some intuitive handle on how they work before delving into the formal mathematics of what we can say about them and what theorems we can prove about them. So my baseline data structure, if you will, is that of a finite topological space. And a nice theorem of Birkhoff that goes back quite far says that if you want to study finite topological spaces, you might as well study finite partially ordered sets or preorders and look at the Alexandrov topology built out of upsets, upwardly closed sets. So for instance, what I have here on this slide is a partial order in which the elements are marked by little blue diamonds. And the order relation, the less than or equal to kind of relation, is marked by arrows. So you can think that the element on the head of the arrow is greater than or equal to an element on the tail. And so I can build a topology on this by way of its base, by stipulating that any upwardly closed set, such as the one I've shaded here, this is the upwardly closed set that starts out at the element I've marked with a red arrow, those are going to form my open sets, and any unions of these are going to form my open sets. It's easy enough to show that this is a base for a topology because intersections of upwardly closed sets are still themselves upwardly closed sets. So you can see here, if I take the two elements marked in red and look at their upwardly closed set and take the intersection, you'll see that, hey, that too is an upwardly closed set. So this forms a base for a topology. This is the underlying topology for all the sheaves that I'll be studying. Now, a sheaf on a partially ordered set, basically it's an object that's got two kinds of data built into it. So to each element of my partial order, I assign a data space. Here I've assigned various real vector spaces, but they could be any pseudometric space you like. These are the stalks. And indeed, these will turn out to be the stalks in the traditional sense of a topological space. They could be measure spaces. They could be more elaborate objects. But for this particular talk, I'm going to be building sheaves of pseudometric spaces on a partial order. And the way that I want to think about them is that they've got some kind of metric on each of these. And those metrics have to be related to one another in a way that's consistent with all of the order relations that are built into that partial order. So the sheaf not only contains the stalks, each of these sets, it also contains restriction functions that follow that order relation. And you should think of it as a restriction because really the data should be thought of as being associated to each of these upwardly closed sets. And the restrictions go from big to small upwardly closed sets. And so for this particular sheaf, I've marked out the restriction maps based on linear maps, i.e. matrices. But they need not be linear per se. They really only need to be continuous with respect to the metrics that I've chosen on each of the stalks. Okay, and the constraint is that this diagram needs to be a commutative diagram, which is to say composition of the restriction functions is path independent. And that's the end of the story. That is a sheaf. Now you might say, well, wait, isn't there some kind of gluing axiom? And the answer is yes. The gluing axiom is baked into how I'm about to build global sections. And the way that I build global sections is by way of assignments. So an assignment is a choice of a value out of each of the stalks, or at least some of the stalks. If you choose a value out of every stalk, sometimes you'll see this called a serration. That's something a bit of a pun for the mathematician Serre. But I think it's a little more opaque. I call it an assignment because I'm assigning values to some of these stalks. Now, the nice thing about assignments to a sheaf is that I can check to see if they're consistent. So for instance, this one is consistent with all the restrictions. So if I take any one of these vectors, values from each of these sets, and pass it through a restriction map, I get the value that's at the end of that restriction map, at the head of it. So for instance, if I start at the very bottom at the vector 2, 3, and I multiply it by, say, the matrix on the very left, the 1 minus 1, I'll get the value minus 1 that's already there. And this happens all over the diagram. If that's the case, this is a global section. And this is how I bring the gluing axiom into the sheaf, is by stipulating that this is what a global section is. Now, in actual fact, I rarely have global sections. Often, I may get partial consistency. So I've marked in red some of the places in this diagram of this assignment in which I don't get the value that's there. So for instance, that 2, 3, if I multiply that 2, 3 by 1 minus 1, I get negative 1, not plus 1. So there's a bit of an error there. This is the way that we represent noisy or erroneous data, or even the model is wrong kind of situations in this context.
And Michael?
Shoot, yes.
Sorry for interrupting, but I assume we are not so many people. So usually a stalk is not a value on an object of a sheaf.
Of course, it's a value on the minimal open set.
Yes, yes. So, but
and I have minimal open sets because I'm in a finite space.
So this is a particular feature of
Exactly.
With sheaves and finite topological spaces.
Absolutely.
Okay, thanks.
You are welcome. Yeah, that's a great question, and that's an important point. It makes my life so much simpler to work on finite spaces, which is why I'm doing it. Okay, now, the point of the matter here is I can measure the amount of error that's present. All I need to do is I need to say, well, the value that should have been propagated into a stalk versus the value that's actually there. Since each of these are pseudometric spaces or metric spaces, I can measure that distance and then aggregate through all of these different possibilities. Here are a bunch of them listed, and figure out just how much error there is. This is a statistical aggregate. So for instance, I could take a max, I could take a median, or various other kinds of aggregates are possible. Trust the statisticians. Choose something reasonable that's not like a maximum, although it's much easier to prove theorems about the maxima rather than something like an L2 norm. Regardless, this quantity I'm calling the consistency radius. The idea being that global sections have consistency radius 0, and the larger the consistency radius, the farther you will have to perturb your assignment to get to a global section. Speaking a bit more precisely, the global section, the distance between an assignment and a global section is lower bounded by the consistency radius times a Lipschitz constant that comes about from the restriction maps. So this gives you a way of identifying how consistent your data are to the model espoused by the sheaf. Now, you might say, all right, how does this work? Is this a reasonable thing? The answer is it's reasonable in a sense because consistency radius is a continuous function of the assignment. So if I move one of these values in my assignment a small amount, it only perturbs the consistency radius a small amount. It also is also continuous in the topology of uniform convergence on the restrictions, which is to say if I perturb the sheaf a little bit about some particular point, then the consistency radius only changes a small amount as well. So this is a reasonable quantity from the standpoint of doing some kind of application-based analysis. Now, why would I do this? Let me give you a fairly concrete example. So my family is very into amateur radio, and one of the things we like to do is go amateur radio fox hunting, which is the goal is find a hidden transmitter. This is not only a lot of fun, it's also kind of useful for training for disaster preparedness. If someone is trapped in a building that something bad has happened to, maybe there's an earthquake, and they've got their cell phone, you want to triangulate their cell phone to find where they are so you can send rescuers to find them. So amateur radio operators practice finding these hidden transmitters. So these hidden transmitters are called foxes, and I've shown you two different foxes here. The Fox A was actually built by my son, who's in the red shirt there. And there we are, finding with various kinds of radio sensors, trying to find a hidden fox. Fox B is one we actually found. Now you have lots of different kinds of sensors. They all work a little bit differently. And you can put together your different measurements using a sheaf. And then by looking at the consistency radius, you can tell how well you're doing at the task of locating the fox. So how does this work? Well, let me take, for instance, a sensor that gives you a bearing, an angle, or a compass direction. Depending on what kind of antenna you use, say, for instance, the top picture there has an antenna that has a very broad radiation pattern. It finds a lot of signal from many different directions versus one that's a little bit more focused like the one on the bottom. It can give you a better bearing. So the amount of error you'll get can vary quite a bit depending on your antenna. Now, these are both idealized. In reality, the radiation pattern can be quite complicated. This is one we measured in the field. But regardless, one way or another, you get some kind of angle or bearing as a function of where the sensor is. In this particular plot here, I've shown you the bearing to the fox, given that the fox is at the origin and you are at one of the coordinates marked here. So you can see as you move around the fox, the bearing that you'll read out very smoothly around, and then there's a branch cut along the top as you flip from 360 degrees to 0 degrees. Now, how do I put this into a sheaf context? Well, the way to do it is actually to use the stalks and the restriction maps to capture the different observations you might make. So for instance, the fox might have a latitude and a longitude. That's a two-dimensional vector. Now, the measurement that I will make, or my son here will make with his radio, is he will have his own latitude and longitude. That's another element of R2. And he'll measure a bearing, an element of S2. Now, what the sheaf models is it's a very model-based approach. And it says, hey, given the fact that if we knew where the fox was and we knew where my son was located, that's an element of R2 cross R2, the fox and the sensor, then I could predict, well, where the fox is by simply projecting out that first component, or I could predict what bearing he should read from that location. And so what I can then do is I can examine how likely is the fox to be at some specific location by looking at the consistency radius on this sheaf. Now, this is not enough to lock down that fox position. We need to take another measurement of some kind in order to lock it down, to, in particular, control the size of the space of global sections. So for instance, if he takes another bearing from another location with a different sensor, we'll have two copies of this diagram. And we can literally just stick them together, glue them together, so that we now have a bigger sheaf. And what you can do is you could drop in the sensor one position and bearing into that particular stalk on the upper left corner of the diagram. And when he takes his second bearing and his location on the upper right, and then you could say, all right, I'm going to look over the entire space of global sections and find me the one that's nearest to that particular assignment. Or conversely, what I could do is I could say, let me scan over the space of assignments to this sheaf, finding the ones that have the smallest consistency radius, such that those two observations he's made, the upper left and the upper right corner of the diagram, are fixed. If I leave those alone, scan over all the other assignments, and find the one that has the smallest consistency radius. What that will do is that will correspond to trying to intersect the sight lines from the two bearings that he's taken, and hopefully find that the fox is there. Now, you might say, yeah, I could have done this by geometry. Yeah, that's true. I agree. But you could also do this same procedure for more complicated sensors that are very different types. And that's where the sheaf idea turns out to be very handy in practice. So just to give you an idea what this looks like, if I sweep around that assignment, I realize the assignment is 6-dimensional. I'm showing you a 2-dimensional slice of it here. You get a minimum consistency radius where those sight lines intersect. That's looking on the left. So I have a sensor placed at one location, a sensor at another location, and the arrows indicate you the bearings that are red there. And you can see right where those sight lines cross, there's a minimum of that consistency radius saying, yep, that's probably where the fox is. Now, this could also identify a situation where you've got a problem. And this often actually happens in amateur radio fox hunting, is that you've got something's gone wrong. Your antenna broke, your sensor isn't getting a good signal, you're getting a reflection off of a building, and so your bearing is crazy. So the scenario on the right, I've got two bearings, the sight lines do not intersect at all. And you will notice that the minimum consistency radius location is not really anywhere on the page. So for instance, if I look at where that star is, the consistency radius is still quite large, and it doesn't have a local minimum anywhere. That's an indication you got a problem. And as you can see right away, okay, the sheaf is telling me I've got a problem. How could I leverage that information to fix the problem? Well, really what you need to do is you need to localize the consistency radius. The consistency radius is a global thing read over the entirety of an assignment. So let's try to localize it. If I just restrict my attention to a shaded set here and say, how consistent is that 1/2? So what I've written here is I've written a sheaf diagram, and I've given you an assignment. The numbers are chosen from values of the stalks. This particular sheaf is just a bunch of stalks that are single real numbers, and the restriction maps are just these linear maps, 1x1 matrices on the edges. So I have an assignment that I've chosen there. You'll notice if I just restrict my attention to the 1/2, there's nothing to compare it to. So the consistency radius for that upwardly closed open set is just 0, because it's nothing to compare it with. By default, it's consistent with itself. If I expand my reach a bit, look at an open set that's a little bigger, you can see that if I take 0 multiplied by 1/2, I get 0. That's not 1/2. It's a distance of 1/2 from 1/2. So the consistency radius on this larger open set is 1/2. Similarly, if I come in from the other side, consistency radius is also 1/2. It's a different kind of thing from the other one, and yet the consistency radius over the whole works is a number yet larger. It turns out that this localized consistency radius is monotonic with the size of the open set. It's not a measure, doesn't satisfy inclusion-exclusion. Turns out to be an inner measure after some amount of work. But this gives you some way of understanding how the data in the assignment are consistent or not with the sheaf. You will notice here that I've got something of a cover that's been labeled up with consistencies. And so this really suggests to me that I ought to filter this cover. And so really, if I start out with a sheaf and I have an assignment, I can cook up a filtration of covers. And by sweeping that threshold of consistency, I pick up more and more open sets. And eventually, I end up picking up them all. Turns out this diagram, which I'm calling the consistency filtration, is itself a sheaf. It's got a weird base space. Its base space is the Alexandrov topology on reals with the partial order, or the partial order given by simply ordering the real numbers. And the sheaf is valued in a sheaf of a category of cover coarsenings, which I'll explain to you in a moment. So this object is kind of strange already, but this actually suggests right away that there's a functorial relationship between the assignments of the sheaf and this consistency filtration. This object is already a functor in a nice way. Now, let me suggest to you that this is not that exotic of an object. And actually, in the TDA community, people study persistent homology all the time. This is related, in fact, to persistent Czech cohomology in this following way. So if I take a point cloud in Rn, I can show you that this consistency filtration is actually a strict generalization of this idea. So here I have 4 points. It's a point cloud. Let's say it's an Rn. Of course, I've drawn it in R2. What you do, yeah, shoot.
Sorry to interrupt.
Go for it.
Go back a couple of slides and just explain that last one more. Yeah, well, the last comment.
Yep.
I don't know what that means. If you could
okay.
just explain it.
So right. So an inner measure does not satisfy the inclusion-exclusion principle. But what it does is it satisfies a bound on the inclusion-exclusion principle, that this value may be unusually large compared to what the inclusion-exclusion principle means. That's what an inner measure is.
Got it. But it still would satisfy things like finite additivity over disjoint sets.
Yes, yes. But the inclusion-exclusion principle does not work.
Okay, great. Thank you.
Yep. Mm-hmm. Okay, so we've got our point cloud. And what I'm going to do is I'm going to build a sheaf on the complete simplex, i.e. the Alexandrov topology on the complete simplex. So you'll notice here that every possible subset of these 4 points is represented here in this partial order. They're ordered by inclusion. So for instance, x1, 2 is included in x1, 2, 3, for instance. Now what you do is, this is the partial order. I'm going to build a sheaf on it by stipulating the stalks. Just pick Rn on each of them, the constant sheaf. So each restriction map is just the identity map. But now the assignment I'm going to put on this is not a global section at all. What I'm going to do is I'm going to drop it to just the bottom layer, the coordinates of each point that I have, leaving the others unspecified for the moment. What I'm then going to do is I'm going to sweep over all possible assignments of this sheaf that have this bottom layer fixed. So the coordinates of each of the points are fixed, and I'm going to sweep over these other guys. When I do that, I now have a global assignment with a minimal consistency radius. Since everything is finite and whatnot, I can do this. This is well defined. And in fact, if I do this all with RNs with Euclidean spaces, there's even a nice way to compute it. And actually, each one of these points now has an interpretation. What I found is I found the circumcenter of each subset of the points. And if I then look at each of these various points and look at their radius, because it's a circumcenter, that radius of each set of points is well defined, what I end up with is the usual Czech filtration that I might want to build. This structure then recapitulates persistent Čech cohomology when I compute the consistency filtration. Now that's kind of neat. So that says that this TDA approach is really actually a special case of this more general sheaf object. Now, one of the things about Čech cohomology is that it's nice from a theoretical standpoint. And most of the time when we talk about Čech cohomology, we talk about good covers. Now, good covers are those in which you essentially just see the topology of the underlying space. The topology of this underlying space is this is a complete simplex, or the face order for that complete simplex. The topology is rather uninteresting. But the cover structure that I get from a filtration can be really interesting. And so I want to study what a filtration looks like, and I want a tool that will really be sensitive to that. So the classic tool for doing this is Čech cohomology, but as I said, it's coarse, and it's actually kind of blind to the cover when you have a good cover. It only sees the underlying space. I'm actually kind of interested in bad covers. And recently, some of my collaborators have been messing around with the combinatorics of cover measures. And they're really interested in understanding how fine is a cover, how overlappy is a cover, and they're kind of different concepts. Fine means all the sets are small. Overlappy means that there's big overlaps between those sets. And you can have covers that are both coarse and overlappy, fine and overlappy, etc. And really their main tool is a theorem of Birkhoff that says the set of covers is ordered by refinement, has an explicit rank function that you can compute. And it will tell you essentially how coarse the cover is. And so if I have an assignment for a sheaf whose maximal cover that I've just built there, or whose consistency filtration, if I look at it, has a very high rank, it means that it's more self-consistent. Now let me delve into those points and really explain them, because it's not really obvious until you played with it. So here are two covers of the set 1, 2, 3, 4, A and B. You'll notice the cover A has got 2 sets in it. The cover B has 2 sets in it. The cover B is both coarser, the sets are bigger, and more overlappy. If I look at all the refinements of A and B and ask how many total sets are involved, you'll notice that that B has got a lot more ways that I can refine it. A doesn't really have that many ways I can refine that strictly. If I count up all the sets for A, I get 6. If I count up all the sets for B, I get more. That's an indication that B is a coarser cover. This is that rank function that Birkhoff is telling us about. Now, in fact, if you go ahead and say, all right, now that's an ordering on covers, I should have a lattice or something like that. And in fact, the answer is yes. Emily Purvine and Cliff Jocelyn recently proved that, that actually there's a lattice of covers. And here are several different covers within the lattice of covers on elements with sets with 4 elements. You can imagine sets with 5 elements, this lattice gets a lot bigger because it doesn't scale exponentially, it scales super exponentially. Because of course I'm dealing with the power set of my set. So I think what Emily told me is that she at one point computed the lattice for 5 and it basically didn't fit on a piece of paper. And for 6, I think it crashed her computer. So this thing scales badly, but it's a useful thing. And they came up with a clever way to compute this rank function pretty quickly, even though computing all of them is kind of nasty. All right, so let's see if we can turn this very quantitative combinatorial thing into something a little more category theoretic. So let me build you a category that I'm going to call PartCovers, which are partial covers of a set. The way you do it is you start with a fixed topological space. So I'm going to put a topology of some sort on the set 1 through 6, the set of integers 1 through 6. The objects in this category are going to be collections of open sets. I'm going to have no requirement of coverage per se. That's the partial in the PartCovers. Those are going to be my objects. So for instance, here are 3 different objects in this category. Each one of them is essentially a set of open sets. Okay, now it's a category, I better tell you what the morphisms are. The morphisms are refinements. So for instance, I can stuff a whole bunch of those cover elements from that second row into the ones in the first. Each one of them is a refinement of the one above it, and so on. So morphisms in this category are refinements. I'm using the script text here to refer to a cover, and refinements then are an arrow. This is refinement in more or less the usual way that you might see if you're playing around with Čech cohomology. But unlike Čech cohomology, no requirement of actual coverage, because they're partial covers. Okay, so that's the category. What can I do with it? Well, for one thing, you can ask is, are there minimal representatives? What do the isomorphism classes look like? Well, the isomorphism classes, each of them have a minimal specification, i.e. an element, a partial cover that is easiest to specify, that has the fewest number of open sets in it. It's called an irredundant cover. So for instance, the guy on the bottom has got that extra open set 2, but it refines into everything else. So I don't really need it in order to specify the cover. So these two guys are in the same isomorphism class. The top one is irredundant, the bottom one is not. And a nice little lemma you could prove is that every finite partial cover, i.e. object in PartCovers, is isomorphic to, in PartCovers, to a unique irredundant one. This relies on the finiteness every which way. So don't ask me what happens if it's not finite. You got problems. Okay, now let's use these ideas. When we're dealing with sheaves and assignments to sheaves, we have these filtrations. So consistency filtration has also got a consistency function attached to it, that local consistency or radius. So let's try to bake that in. So let me make a fancier category, a category of coarsening filtrations that I'll call CoarseFilt. An object in CoarseFilt is a chain of morphisms in PartCovers, so a sequence of refinements of these partial covers, that is ranked by a monotonic height function. So that height function then says, all right, at height 0, I get one of these guys. At height, say, 1/2, I get another one. And at height 1, I get another one. And so as I go bigger, I coarsen, or as I go smaller, I refine. For instance, this could be that cover lattice rank given by that Birkhoff theorem, but it need not be. It could be something else. In fact, I'm really thinking of that consistency filtration, local consistency radius here. Okay, so those are the objects. Now, what are the morphisms? Well, the morphisms between these things have to be a sufficiently sort of elaborate object to link together all of the different pieces of data that are in these elaborate objects. So what a morphism is going to have to be is not only is it going to have to deal with refinements between these covers, but it also has to manage that height function in a reasonable way. And so what I'm going to say a morphism in this category must be is it must be a monotonic mapping of that height function such that when I map it that way, I get refinements the other way. So it essentially is telling me how to co-refine these covers in a nice way. And by in a nice way, I mean this kind of diagram of refinements needs to commute. So for instance, if I refine down and then across, it's the same as refining across and then down. And which refinements I do across are governed by this monotonic mapping function. The reason for all of this messing around with this monotonic mapping function is because it plays well with the underlying consistency function structure that works with the sheaf. Now, this is a category, but it actually also is a metric space on its own too. CoarseFilt has this dual nature. It's both category and topological space. And actually one of the nice things that's been showing up in the TDA literature is this notion of an interleaving distance. That works here too if you generalize it appropriately. So if I have two morphisms that kind of go in opposite directions, so I have a pair of morphisms, i.e. pair of monotonic mappings with all these various refinements going both now across both left and right. So all of these diagrams commute appropriately. And then I ask, well, how much if I try to go bounce from left to right? That's not required. If I go from left to right, back to left, or the other way around, from right to left to right, that's not actually required to commute. So if I take a look at the amount of distance that's happened there, that gives me an interleaving distance, as in how far have I traversed in height, in the height function when I do that. If I bound that, and then do a minimax over that, that gives me a metric. And that metric we'll call the interleaving distance. It turns out that this is just the right thing we need to do in order to show that the consistency filtration for assignments is actually a continuous function. So to come back to that point, if I take my sheaf assignment, build out this diagram, which remember I've got a sheaf, an assignment, and that thing now is a coarsening filtration, as we've gotten. I could have underlying sheaf morphisms under the hood. Those guys, if I perturb the sheaf a little bit, hey, it's going to drag around those consistency filtrations. And in fact, the theorem which I've proven in this paper is that actually this is continuous when I use the coarsening filtration interleaving distance. As a side effect, we proved something we already know, which is persistent Čech cohomology is also a stable object as well. So that's pretty neat and pretty handy. So how does this work? Well, if I perturb my sheaf and my assignment by a small amount, so you'll notice here the left and the right are two sheaf assignments, two slightly different sheaves. So you can see that I perturbed the top guy by 0.1, 0.5 versus 0.6. And I've also perturbed that restriction map going from bottom to top, 0.8 versus 0.1. So I perturbed both the sheaf and the assignment, of course, subject to both of them being sheaves. That small perturbation gives me two different consistency filtrations. I've kind of rendered them in summary here. If I go ahead and look at the interleaving distance for their coarsening distances, I can refine them to one into the other. I can bound the amount of displacement that I get in local consistency, and that bounds the interleaving distance. That's kind of how this works. Now, you might say, that's pretty cool. What about functoriality? It's got this dual nature. Are they really? Well, I have to make a notational apology here. The category that you want to be working with is the category of sheaves on these finite spaces with pseudometrics paired with assignments. I call it Shiv FPA for lack of a better term because I can't think of one, sorry. But this is a pretty crazy category. Not only is it the category of sheaves as you might be used to, it also drags around the assignments, and I permit the base spaces to change. So there's a lot going on in this particular category. And if I had more time, I'd prove for you that this category actually, when I use it, makes the consistency filtration into a covariant functor. Have a look at the paper, and you can see the proof there. It's actually just an elaborate diagram chase. It's not too terribly enlightening once you have all the pieces in place. Coming up with the right definitions is always the difficult part here. But what I'd like to do is actually I'd like to kind of fill a gap. The consistency radius and the local consistency radius, that's continuous, but it's not functorial because there's no real right category for it. But what I'd like to do is actually show you that there is a right category to work with, and it's sort of a more exotic category. And mostly in the theme of playing with shiny category theoretic objects, it's just the thing to fill that bill. So the local consistency functions, i.e. labeling up my assignment in the middle here that we've been looking at before with the local consistency radius for each open set, with that local consistency radius, I'm going to call that set of consistency radii written out here on the right an object in a category I'm going to try to define called con, which is the category of consistency functions. Now, I'm going to defer for a moment telling you what the morphisms in this category are, because they're pretty exotic. Ideally, what we're going to want is we're going to want the consistency radius to be a functor from the category of sheaves on finite pseudometric spaces with assignments into this category con. And I'm going to want to be able to cook up the consistency filtration, i.e. functor from con to CoarseFilt, that works by thresholding. So if I draw a line in the sand and give me all the guys that are consistent to 1/2, I'll get the two sets AC and AB as I've got here. Okay, that's what I want. In order to do that, the morphisms in the category con have to be a little bit weird. They're actually given by non-negative real numbers that bound your ability to stuff one consistency function as a lower bound in the other. And composition works by multiplication. This is really weird. Let me show you by example, because it's really kind of easier to think about it. If I take the object on the right, okay, that's the one we've had before. If I look at the object on the left, every local consistency radius, i.e. every number in the corresponding location, is the one on the left is bigger than the one on the right, greater than or equal to. So 0 is less than or equal to 0, 1/2 is less than or equal to 1/2, 2/3 is bigger than 1/2, and 1 is bigger than 2/3. So that means that there's a morphism 1 that goes from right to left. There's also a morphism 1/2, 2, 3, and so on up the chain. Fine. This category's got a lot of morphisms in it. There's also a morphism 2 going the other way. Basically what you do is you make the guy on the right bigger by a factor of 2, and that everything from the left fits inside the right, as in it's less than or equal to. But oddly enough, if you wanted an isomorphism between these guys, you'd need to be able to multiply them by a half, and neither of those work. So these guys are not isomorphic in this category. And the reason for that essentially is that they don't actually have reasonably isomorphic coarsening filtrations. But it turns out that this category con is equivalent to a subcategory of this coarsening filtration by way of two functors, one by thresholding, which is faithful, and one which is non-faithful, which goes the other way. And so the interpretation here is that you could summarize the filtrations of partial covers using these consistency functions, but you lose information when you do that. Let me show you how this works really briefly and graphically. So if I have an object in con and I threshold it, I'll cook up an object in CoarseFilt just by saying, okay, pick a number between 0 and say 1 and give me all the sets that are less than or equal to that. So for instance, if I pick 1/2, I'll get AC, I'll get C as well, but I won't get the BC because that's got a 2/3 on it. I won't get ABC because that's got a 1 on it. And I'm showing you here one of the isomorphism classes in CoarseFilt, just because that makes it a little easier to draw. Okay, and morphisms go the way that they should. This is why the morphisms in con are wacky, because the morphisms in CoarseFilt are these monotonic mappings. And essentially what you're doing is you're scaling that monotonic mapping by a factor of 1/2. That's what happens. And then the refinements work just fine. This is a faithful functor. Now going the other direction first seems pretty easy. If I have an object in CoarseFilt, that's this coarsening filtration labeled up, and I want to know what value should go on a particular set, say AC, what I should do is just look up its value that set first shows up. In the persistent homology mindset, I'd say, find me the birth time of this set. And the birth time, say, of AC is 1/2. So I'll put in 1/2 there. That seems pretty easy. And then after thinking about it, you say, wait a moment, what happens about irredundancy? What if I have an irredundant cover? Well, this kind of makes things messed up, except for the fact that if I take the smallest threshold where that open set is contained first in a particular cover element, any cover element, it turns out that that's fine. So it actually is not, there's not really a problem. It is well defined. And the morphisms drag along just as you might expect, with one little caveat. So the morphisms in CoarseFilt are these functions phi. If I look at them, they're monotonic functions. And so as my calculus students will know, I should probably be thinking about Lipschitz functions. And so assuming I got a Lipschitz function in hand, I can use that morphism in con. That real number is essentially 1/, the Lipschitz function for a constant of the Lipschitz constant of 1/phi, assuming that exists. So the problem with that assuming that exists caveat means that this is not a faithful functor, and it actually requires a little bit of limitation exactly on what part of CoarseFilt you use. So actually I'm lying a little bit. You need a subcategory of CoarseFilt to make this work. But okay, fair enough. So wrapping up, the assignments to sheaves can be studied using both the topology, the metrical side of things, and the category side of things, the functoriality. The main tools for doing this, and they're quite practical, are the consistency radius and the consistency filtration. Although the consistency radius itself isn't functorial, there are fancier invariants like this consistency function category, this con, that are. And so as an open question, maybe we can relate the local consistency structure of a sheaf assignment to actually the structure of functions on the base. Then it would feel very much like more a typical sheaf theoretic kind of way of looking at the world, where you study, say, a sheaf of functions on some manifold or something like that. These may be related, but since everything in sight is finite, I don't know. And so hence an open question. So that's the end of my talk. I hope this was interesting and perhaps exciting. I am always open for questions, especially right now. We've got some time for that. Drop me an email, have a look at my website, read some papers. And as I said, and as Brendan said at the beginning, the main reference to all the theorems proven in this talk, or at least that I advertised, are in this paper up on compositionality. And if you happen to be a hacker and want to write some code, my Python library PySheaf up on GitHub perhaps is just what you're looking for. So thank you.
Great. Thanks. Thank you, Michael, for a wonderful talk. As mentioned, we now have a bunch of time for questions. If you'd like to ask a question, you can write in the chat or raise your hand and I'll get to everyone in order. To begin, over on the Zulip chat, Brian Pinsky asks 2 questions, one from early in the talk. You mentioned the distance between an assignment and a global section.
Yes.
Are you taking the product metric to give a sensible notion of distance between assignments?
Absolutely. Yeah, the product metric is necessary. There's some ambiguity in what the product metric is. Statisticians know and love the fact that different choices for that product metric will give you different outlier performance. And so as a practical matter, choosing the right product metric, i.e., do you want to aggregate by L2 or do you want to aggregate by L1 if you're into sparse stuff? That all has computational and application implications, but yes.
Okay, thanks.
Mm-hmm.
And a second question, the construction, this is again from Brian Pinsky.
Yes.
The construction you're giving for CoarseFilt feels a bit like taking the nerve of part cover.
Yeah.
Is there a way of expressing that connection?
I bet there is. I have not sat down and tried to tease that out explicitly, but yeah, that was actually kind of my motivation for writing it that way in the first place. It's kind of inspired by that.
Okay, great. Any other questions? Well, one question I have, maybe naive from the last part of your talk, you talked about functors in each direction between con and CoarseFilt.
Yes.
Do these form an adjunction?
I am suspicious that they might, but I haven't successfully proven or disproven that. I think a few good examples would probably tease that apart.
Mm-hmm.
It really feels like they ought to be, but you know, as I said, I haven't sat down and gotten to the bottom of that.
Okay. Any other questions? Okay, well, if there are no further questions, let's thank the speaker again. So
Thank you.
thank you, Michael.
My pleasure.
For joining us. It was a wonderful talk.